Okay, so I talked about making this screencast to give you an overview of acids and bases to help you as you work through one of the first problem sets that we're dealing with in AP Chem. So let's get started with it. So fundamentally what we have to remember is some definitions. So when we talk about something being an acid, we have to remember that an acid, based upon the Bronsted-Lowry definition, is going to be a proton donor. And a base is going to be a proton acceptor. So these two fundamental definitions are going to drive everything that we look at from here on out. Some other things that we need to make sure that we're comfortable with are key terms of strong versus weak. And we can say something is a strong acid or a strong base, and we can also say things are a weak acid or a weak base. And what that fundamentally tells us is not how dangerous the chemical is, but more so how far it dissociates. So if we say that an acid is a strong acid, and some examples of strong acids are HCl, H2SO4, HNO3, HBr, HI, and some others, but these are the most common ones. What that means is that the equilibrium position for these acids lies so far to the right, to the product side, that essentially they dissociate 100%. So when we say something is a strong acid, that means that it dissociates 100%. So for every molecule of acid, we're getting a proton that's available. And the converse is true for a base. If we say that a base is a strong base, and examples of strong bases would be group 1 metal hydroxides, and a couple of group 2 metal hydroxides, but you'll most typically see group 1 metal hydroxides. That also means that if it's a strong base, it's going to completely dissociate into ions in solution. So from here, what I thought would be helpful is if we actually start to look at some things that aren't strong, and in any sense of the word, whether a strong acid or strong base, and start to look at some things that are weak acids and weak bases and what that means. So what we're going to start talking about first is a weak acid. And for a weak acid, what we have to remember is, and I'm just going to choose acetic acid because it's a very common weak acid that you'll see all the time. A weak acid really is essentially a equilibrium situation. So the formula for acetic acid, HC2H3O2, that means there's an equilibrium position set up where it dissociates into a proton or hydrogen ion and the acetate ion. And this specific equilibrium process is given a very unique equilibrium constant, and we call that equilibrium constant Ka because it's dealing with a weak acid. If it was a weak base, you would be dealing with Kb. And the Ka for this process just happens to be 1.8 times 10 to the negative fifth. When you see a number like this lets us know that not a whole heck of a lot of acetic acid is going to dissociate at these particular temperature constraints to form protons and acetate ions. So the reason why we might want to know this information is oftentimes to calculate another value, and that value is called pH. The way that we calculate pH is based particularly upon the concentration of one ion, this hydrogen ion concentration itself over here. So for a weak acid, we can't make some assumptions that we can make with a strong acid. So for example, if you have a strong acid, you can assume 100% of the acid dissociates. That makes it very easy to calculate hydrogen ion concentration and very easy to calculate pH. But for a weak acid, we have to use the equilibrium expression to solve for H+. And in either situation, we use the same equation to calculate pH. pH is just based upon the negative log base 10 of the hydrogen ion concentration. So if we know that information, we can calculate the pH of the solution. Of course, we would have to know the concentration, and we would have to know Ka. So let's look at an example where that information is given. So imagine that I took a beaker, and inside that beaker, I put some solution, and I poured in 50 milliliters. So we have 50 milliliters of 0.75 molar acetic acid. And then the question is, well, what's the pH? To solve this problem, we have to start by setting up an equilibrium equation. And then from there, we're going to plug in some values and use an ice table to solve the problem. So the first thing is we have to know what we're dealing with. So we're dealing with acetic acid, HC2H3O2, dissociating into the hydrogen ion and the acetate ion. If we remember when we set up an ice table, we always want to know the initial, the change, and then the equilibrium. So for this particular problem, before equilibrium is established, we know that we have 50 milliliters of a 0.75 molar acetic acid solution. So initially we have 0.75 molar acetic acid. None of it's dissociated into ions just yet. We know that at equilibrium, some of it will dissociate, and that amount will be some amount X. Now the amount that forms hydrogen ions will be positive X. So at equilibrium, our equilibrium concentration will be 0.75 minus X, and then X and X. Now at this point, it's worth noting a couple of things. If you look at the Ka value, and the Ka value for this process, remember, is very small. When we set up our equilibrium expression using Ka, we'll notice something that we might be able to take into effect. So I'm going to take this information here and transfer it to the next slide. So our equilibrium concentrations are going to allow us to set up a situation that looks a lot like this. Ka equals the concentration of hydrogen ion, which would be X, the concentration of acetate ion, which is also X, over the concentration of the undissociated acetic acid, which in our case is 0.75 minus X. Now here's something that's important. This amount X compared to 0.75 is going to be very, very small. So small that we can essentially make this statement. We can say that there is approximately equal to X times X over 0.75. And the reason why we can do that is two things. One, our Ka value is very, very small. Second, the concentration of our acid is relatively significant. 0.75 molar solution is reasonably concentrated. So this amount X compared to what we're starting with is going to be insignificant. But notice, however, that we don't consider the X's for the products to be insignificant because there was 0 to begin with. So any value X compared to 0 is going to be significant. So the simplification we're making here is one that is quite reasonable. We can assume that this X is insignificant because we have a high concentration and a relatively small Ka value. Something on the order of 10 to the minus fifth, 10 to the minus fourth, a very, very small value. And that helps us in terms of our solution for this particular problem. So we plug in our values, 1.8 times 10 to the minus fifth equals, and I'm going to combine some terms here, x squared over 0.75. And then we get a value for x equal to 3.67 times 10 to the minus third. And that would be the concentration in molarity. Now that X, remember, equals the concentration of hydronium ion, the hydrogen ion, as well as the acetate ion. And fundamentally, if we go back to the slides that we were dealing with, we have to remember that we were trying to find pH. So pH is the negative log base 10 of the hydrogen ion concentration. So now we can set up this equation and actually solve. So we take the negative log of 3.67 times 10 to the minus third, and we can get our pH value. And the pH in this case would be 2.43. So the previous example dealt with a very straightforward weak acid situation where we calculated the hydrogen ion concentration and then found the pH based upon that. Well, let's make it a little more difficult. So let's say we have that container from the past problem that contains 50 milliliters of 0.75 molar acetic acid. But now let's add something to it. So let's add in to that solution 25 milliliters of a 0.75 molar strong base. And the strong base will use potassium hydroxide. We should be able to recognize that whenever you put an acid and a base together, you're going to get a chemical reaction. And the chemical reaction in this case specifically would be the acetic acid reacting with the strong base to produce a salt. In this case, the salt is going to be K potassium acetate and water. So the general format when you have any acid-base reaction, acid plus base gives you a salt of the acid base and water. So this reaction, notice I didn't draw a double-headed arrow. This is not an equilibrium reaction. Every single drop of potassium hydroxide that I add to this acetic acid solution is going to react. And it's going to form a very soluble salt. Acetate makes very soluble salts, and group 1 salts are all soluble anyways. So we form this potassium acetate and we form some water. So this process is a process called neutralization, and this process is something that you do very commonly in an acid-base titration situation. So this is our scenario. Now we can ask the same question. Well, what's the new pH of the remaining solution? And what we have to remember is some of that acid has been neutralized, but not all of it. And here's how we know not all of it has been neutralized. Notice that I made this problem so that both the acid and the base are equal in concentration. Their molarities are the same. And that gives us a nice baseline in terms of comparing volumes. In order to completely neutralize all the acetic acid, I would need 50 milliliters of the base. But I only have half that much. So we would expect our solution to still be acidic. That also means that we're going to have a significant concentration of acetate ion, what we'll tend to call a common ion in this case, because this acetate ion is common to both this process as well as the equilibrium acid dissociation process for acetic acid. So let's look and see how this changes the problem. First thing we have to recognize is any amount of base that I add, any amount of strong base, I should say, that comes in contact with the acid will react with it completely. All of this salt will remain dissolved in solution. So what we have to recognize is we initially started out with 50 milliliters of 0.75 molar acetic acid. If we convert that into moles, what we recognize is that we have 0.75 0.0375 moles of acetic acid. That amount gets cut in half by the amount of base that we add. So this amount over 2 gives us the amount that we still have remaining. And when you calculate that, you get it to be 0.01875 moles. Now, what we also have to remember is, in order to plug this into an equation or use it in an equilibrium process, we'll have to have this in molarity. So at this point, it's a good chance to be able to say, okay, this number of moles is dissolved in a new volume. Notice that we've got not only 50 milliliters, but now an additional 25 here. So that makes it a total of 0.075 liters. And what you get there is the concentration of acetic acid after this reaction is approximately a third of what it was before. And that takes into account the volume change as well, because you might just assume, oh, it's half the concentration, but don't forget that we're changing the volume as well. So in that case, that makes it 0.25 molar. Okay, so where do we go from here? We've found the amount of, or the concentration of the acetic acid that remains, and all of the potassium hydroxide has been consumed because it's the limiting reactant in this particular process. So now let's go and set up another ice table. So all of these values are going to be really important. So we're going to draw from them as we make our new ice table on the next slide. So again, this process at this point, because potassium hydroxide was the limiting reactant, the pH is still dominated by the weak acid concentration, because that's what's present in excess. So that means that forefront in our mind needs to be this process. The equilibrium dissociation between acetic acid, a proton, and the acetate ion. All of these are aqueous. I'm just not showing them anymore. Again, we're going to set up an ice table now. The key thing that's different, we have to think very carefully about how things have changed and any common ions that may be present in the solution from the reaction between potassium hydroxide and acetic acid. So we're going to walk through this pretty slowly to make sure that things make sense. So remember that we just calculated that the concentration of acetic acid initially would be 0.25 molar. So we're going to make the assumption that this is not at equilibrium yet. So we have no hydrogen ions that have meaningfully dissociated. Now here's the piece where we have to be very careful and think carefully. This concentration of acetate ion, we have an initial amount, and that initial amount comes from the products of the reaction between potassium hydroxide and the acetic acid. And if you do that, you'll notice you have 0.01875 moles of acetate ion that would be produced. And it's dissolved in 0.075 liters of solution, so it is actually the exact same concentration in this problem as the acetic acid. Now, at equilibrium, we're going to expect that some of this acetic acid will dissociate, some amount X. That means some hydrogen ion will be produced and some additional acetate will be produced. So at equilibrium, 0.25 minus X, X, and 0.25 plus X. Now here's where we can also make some assumptions based upon relative concentrations. We know that this amount X is going to be very, very small. Again, because the Ka of acetic acid is very, very small. Now we have to think, where would this matter? Where would this small amount not matter? In terms of this situation for acetic acid, The X is insignificant. We can ignore it. But in terms of hydrogen ion, it's extremely important. We cannot ignore it. For the acetate ion, again, very, very small compared to 0.25 molar. We can ignore it. Based upon that assumption, those assumptions, we can set up our equilibrium expression to look like this. Our Ka value, which is 1.8 times 10 to the negative 5, equals hydrogen ion concentration, which is X, acetate ion concentration, which we're simplifying to 0.25 instead of 0.25 plus X, and our acetic acid concentration, which we're simplifying to 0.25. Notice that these two values cancel, and we get an X value, which is our hydrogen ion concentration, of 1.8 times 10 to the negative 5th. We can now calculate pH. pH is the negative log base 10 of the hydrogen ion concentration. So that's the negative log base 10 of 1.8 times 10 to the negative 5th. And you get a pH value of 4.74. Now, if you're dealing with a weak base, the process is almost identical. The only difference would be, instead of calculating pH values, you would have to calculate pOH values. But as far as the equilibrium processes go and the chemical reactions go with the strong acid, the fundamental principles are the same. So let's spend our last couple of minutes just going over some relationships between pH and pH. So here are these relationships that you need to know. We've already established that pH is the negative log base 10 of the hydrogen ion concentration. pOH is very much the same type of thing, except for the base particle, the hydroxide ion concentration. There are some other relationships here that will allow you to solve for a wide variety of problems, and one of which is most important and most useful is the pH plus the pOH value always adds to 14. And this can be helpful if you're dealing with a weak base problem where you could find the pOH, and then you could use that to solve for the pH value. I think that's good for tonight. Take time, go back and watch other portions of this as you're working through the review problem set. And in class tomorrow, we'll discuss any additional questions that may come up. Have a great night.